Welcome to Cosmic Whispers, where cosmic mysteries come alive. Your journey beyond the stars begins now. What if the most powerful explosion in the universe wasn't a supernova, wasn't a gamma-ray burst, but a collision between two objects so dark, so dense, and so mysterious, they bend the very fabric of reality? Imagine two black holes, each a remnant of a once massive star, collapsed into a point of infinite density, caught in a cosmic spiral. For billions of years, they circle one another in silence, their immense gravitational pull drawing them closer with every orbit. And then, when they are only a few hundred kilometers apart, gravity takes over completely. The two black holes accelerate to half the speed of light, the space around them distorting like a lens made of liquid, and in a final, violent instant, they merge. No light is emitted. No shockwave tears through a nebula. But from that cataclysm erupts something far more mysterious. Gravitational waves, ripples in the fabric of spacetime, burst out in every direction, traveling across the cosmos at the speed of light. These aren't just explosions. They are reality itself trembling. This is the story of black hole collisions, the universe's most violent and enigmatic events. They are invisible to the naked eye, undetectable by traditional telescopes that rely on light, X-rays, or radio signals. And yet, in the past decade, we've begun to hear them. In 2015, an experiment that spanned 2 decades and billions of dollars paid off when scientists at LIGO, the Laser Interferometer Gravitational Wave Observatory, detected the very first gravitational wave from a black hole merger. The signal came from two black holes, one 29 times the mass of the Sun, the other 36 times the mass of the Sun, that collided over 1.3 billion years ago. At the moment they fused, they converted roughly 3 solar masses directly into energy, not as light, but as gravitational waves. For that brief flash in cosmic time, the event released 50 times more power than the combined light of all the stars in the observable universe. And yet it passed through the Earth completely unnoticed by our senses. The LIGO detection was a revolution, a scientific milestone on par with Galileo pointing a telescope at the sky or Edwin Hubble discovering the expansion of the universe. Suddenly we were no longer deaf to the gravitational music of the cosmos. Right now, Cosmic Whispers is just beginning, and your support means everything. Every great journey starts with a few brave explorers. If you enjoy unraveling the mysteries of the universe, hit subscribe. It's free, and it helps us grow this community together. Since that first discovery, dozens of black hole collisions have been detected by a network of observatories. LIGO in the United States, Virgo in Italy, and more recently, Kagra in Japan. Each detection gives us a new piece of the puzzle. Some collisions involve black holes 10 or 20 times the mass of our Sun, while others hint at objects 50, 70, or even 100 times more massive. These events challenge our understanding of how black holes form. Are these black holes the remains of massive stars that collapsed in isolation? Or did they grow over time by consuming gas and merging with other black holes in chaotic environments, like globular clusters or galactic centers? The origin stories are as varied as the events themselves. Some black hole pairs may have been born as massive stars, orbiting each other in a binary system. Over millions of years, they live, burn, die, and collapse together, first into neutron stars or directly into black holes. Others may be wanderers that found each other much later, pulled together by the dense gravitational chaos of a star cluster or accretion disk surrounding a supermassive black hole. In some regions of the universe, these mergers may happen frequently. In others, they may be once-in-a-galaxy lifetime events. But how do we actually hear them? Gravitational waves are unimaginably subtle. When a wave passes through Earth, it stretches and compresses space itself by less than the width of a proton. LIGO detects this shift using twin laser beams shot down 4-kilometer-long vacuum tunnels. If the distances in the tunnels shift, even slightly, it changes the way the beams interfere when they meet again. That difference, just a fraction of a wavelength of light, is the signature of a gravitational wave. And then comes the sound. When we convert the data into audio frequencies, we get a chirp, a rising tone that climbs in pitch and ends in a sudden silence. It's eerie, beautiful, and utterly profound. That chirp contains information, the size and spin of each black hole, the distance of the event, and the moment they fused. It's as if the universe itself whispered a secret across billions of years of space. One particularly fascinating aspect of these collisions is the idea of ringdown, what happens after the black holes merge. The newly formed black hole is initially distorted by the violence of the impact. Like a struck bell, it vibrates and sends out gravitational waves at specific frequencies, called quasi-normal modes. These frequencies are determined solely by the black hole's mass and spin, making them a direct test of Einstein's predictions. If those frequencies ever deviate from theory, it could mean new physics. Some black hole collisions are even more bizarre. In 2020, LIGO and Virgo recorded a merger where one object was around 2.6 solar masses, a number right in the so-called mass gap between known neutron stars and black holes. Was it the heaviest neutron star ever observed, or the lightest black hole? That mystery remains unsolved. Others, like the one known as GW 190521, involved a black hole over 85 times the mass of the Sun, something that standard stellar evolution says shouldn't exist. These discoveries are reshaping our models of how stars die and how black holes are born. And then there's the future. With new detectors like the Einstein Telescope and Cosmic Explorer on the horizon, and space-based observatories like LISA, Laser, Interferometer Space Antenna, scheduled for launch in the 2030s, we'll soon be able to detect black hole mergers across the entire observable universe. LISA will even allow us to hear supermassive black holes, millions of times the mass of our Sun, merging in distant galaxies. These epic fusions, visible in gravitational waves months before the final collision, could provide the clearest tests, yet of general relativity and perhaps even clues to quantum gravity. Black hole collisions are not just cataclysms, they are cosmic laboratories. Through them, we can study matter at extremes of density, gravity at its strongest and space-time at its most distorted. They could even help explain where the universe's heaviest elements come from, or reveal the nature of dark matter if hypothetical. Black holes from the early universe, called primordial black holes, are found to be involved. We are at the dawn of this new science. Each collision we hear is not just a data point. It's a voice from the deep past, echoing through the void, telling us what the universe is made of, how it works, and what it once was. Imagine standing on the edge of a great abyss, not one, of water or earth, but of space-time itself. In front of you, two titans swirl in darkness, invisible yet massive enough to trap even light. You cannot see their form, but you can feel their presence, like a gravity well pulling at the very essence of reality. These are black holes, and when they collide, the cosmos doesn't just change, it reverberates. But where do these monsters come from, and why do they sometimes find one another in the vastness of space? To understand black hole collisions, we first have to understand the birth of black holes themselves. Picture a massive star, perhaps 20 or 30 times more massive than our Sun. For millions of years it burns brightly, fusing hydrogen into helium, then helium into heavier elements like carbon and oxygen. But there's a limit. Once the core becomes iron, fusion stops. There's no more energy to push outward against the force of gravity. In a moment, the star's core collapses under its own weight. The outer layers explode in a supernova, and what remains behind depends on the mass of the core. If it's massive enough, it collapses into a singularity, a point of infinite density surrounded by an event horizon. This is a stellar mass black hole. Now imagine two such massive stars, born from the same cloud of gas, orbiting each other in a cosmic dance. They evolve side by side, live fast and die young. Each ends its life as a black hole. If their orbit survives the chaos of stellar death, they are left circling one another, slowly spiraling closer over billions of years. These binary systems are incredibly rare, but over the vast scale of the universe they are inevitable. Yet this is only one path to collision. Some black hole pairs may be born far apart, only to meet much later in life. Deep in the heart of dense star clusters, where thousands of stars pack into a single light year, Black holes can wander and interact gravitationally. Two solitary black holes might find themselves caught in a chaotic gravitational embrace, flung together through a process called dynamical capture. Unlike the neat circular orbits of stellar binaries, these encounters can be violent and eccentric, colliding within a few orbits, unleashing an intense burst of gravitational waves. Other collisions may occur in the swirling disks of gas and dust surrounding supermassive black holes, the so-called accretion disks found in galactic cores. Here, small black holes can sink into the disk, slow down, and pair up due to friction and mutual gravitational pull. It's like cosmic matchmaking in the heart of chaos. These environments may be the birthplaces of some of the most massive mergers we've detected. But how do we know which path a particular black hole took to its doom? Scientists look to the data encoded in gravitational waves. The shape and frequency of a wave can reveal the black hole's masses, their spins, and even whether they were aligned or tilted. For instance, in isolated binary systems, those born together, spins tend to be aligned. In dynamically formed systems, those that met later, spins are often randomly oriented. Like fingerprints at a crime scene, gravitational wave patterns tell the story of what happened long before the explosion. Let's revisit one of the most intriguing cases, the GW1905-21 merger. Detected in May of 2019, it involved two black holes, one with 85 solar masses and the other with 66 solar masses. When they collided, they formed a single black hole of 142 solar masses, marking the first direct observation of an intermediate mass black hole. This discovery was shocking. Traditional stellar evolution models say that stars cannot produce black holes between 65 and 120 solar masses due to a phenomenon called pair instability supernovae, which completely blow apart the star, leaving nothing behind. So where did these giants come from? The leading theory, hierarchical mergers. Perhaps the 85 solar mass black hole was itself the product of an earlier merger, two smaller black holes that collided and formed a larger one. Over time, in the dense gravitational jungle of a star cluster or accretion disk, these black holes could continue to merge step by step until one massive enough to break the rules was born. If that's true, we may be witnessing the growth of the universe's most elusive giants, intermediate mass black holes, long theorized but only now confirmed. Even stranger is the case of GW190814, where one of the objects appears to be just 2.6 solar masses. That puts it squarely in the so-called mass gap between neutron stars and black holes. Neutron stars, the collapsed cores of less massive stars, top out at around 2.2 to 2.5 solar masses. Black holes, by contrast, are thought to begin at about 5 solar masses. What is this object? A featherweight black hole, an ultra-heavy neutron star, or something entirely new? We don't yet know, but the answer could redefine the line between life and death for stars. These questions are more than academic. Black hole collisions are windows into the unseen, into stellar lives we cannot observe directly, into cosmic environments we can barely imagine. They tell us how stars are born and how they die, how galaxies evolve, and even how the universe grows. And with each new detection, we refine our models. The technology to listen to these events is evolving rapidly. LIGO and Virgo are being upgraded with more sensitive mirrors, better seismic isolation, and new quantum techniques to reduce noise. Kagra, buried under a mountain in Japan, adds a crucial third ear to the network. The more detectors we have, the better we can triangulate where in the sky a merger occurred. That's vital for multi-messenger astronomy, where gravitational wave detections are followed by searches for light, X-rays, gamma rays, or neutrinos. In 2017, this happened for the first time. Though not a black hole collision, the merger of two neutron stars, detected as GW170817, was also seen in gamma rays, optical light, and radio waves. It was the birth of a kilonova and the source of heavy elements like gold and platinum. Scientists are now watching and waiting for the day when a black hole merger happens close enough or with enough matter around it to produce a similar electromagnetic echo. But even in silence, black holes speak. Each chirp we hear is a puzzle piece, and together they form a grand cosmic picture, a story written in space-time itself. Far from the peaceful silence we often imagine in space, black hole collisions are anything but quiet. They are roars in the fabric of the cosmos, vibrations that travel not through air but through space-time itself. These events don't emit light, but they send out ripples that stretch and squeeze the very geometry of the universe. And we can now hear them, literally. But to appreciate how extraordinary that is, we need to understand what gravitational waves are, and just how we came to detect them. Let's begin with Albert Einstein, specifically with his theory of general relativity in 1915. He proposed something radical. Gravity is not just a force, but a bending of space-time. Massive objects like stars and black holes curve the space around them, and other objects move along those curves. But in 1916, just a year later, Einstein realized that this fabric could do more than bend. It could ripple. He predicted that accelerating massive bodies, like orbiting stars or colliding black holes, would create waves that travel at the speed of light, disturbances in space-time itself. These were gravitational waves, but for a century they remained theoretical. Why? Because they are unimaginably faint. Imagine a wave traveling through Earth from a collision billions of light-years away. By the time it reaches us, it stretches the entire planet by less than the width of a proton. That's 1/1000th the size of an atomic nucleus. It's like trying to measure the wobble of a ruler on the moon using a laser pointer from Earth, and yet humanity did it. The breakthrough came on September 14th, 2015. A chirp. That's how scientists described it. A rising tone lasting just a fraction of a second. But that chirp represented something incredible. Two black holes, one with 29 solar masses, the other 36, had spiraled into each other and merged, 1.3 billion light-years away. That collision converted the mass equivalent of 3 suns directly into gravitational energy, radiated outward as waves. It was the first direct detection of gravitational waves, and it changed everything. The detectors that made this possible are called LIGO, short for Laser Interferometer Gravitational Wave Observatory. There are 2, one in Hanford, Washington, and another in Livingston, Louisiana. Each uses laser beams shot down 4-kilometer-long vacuum tunnels, reflected by mirrors at the ends. The idea is simple, but ingenious. If a gravitational wave passes through, it slightly changes the length of one arm compared to the other, causing the laser beams to interfere differently. That difference is what scientists detect, but detecting such a minuscule effect requires isolating the equipment from every other possible disturbance: traffic, earthquakes, even quantum-level fluctuations. That's why the system is built with advanced seismic isolation, suspended mirrors, and ultra-precise lasers. When the first signal was found, teams of scientists spent weeks trying to prove it wasn't real, eliminating every possible error before finally accepting the truth. Einstein was right. Since then, dozens more black hole mergers have been detected. Each one is a symphony in the gravitational wave sky. Some are short and loud, involving massive black holes that merge quickly. Others are more drawn out, their waves slowly increasing in frequency and amplitude as the orbit decays. The shape of these signals tells scientists everything, from the mass of the black holes to their spin, distance, and even the nature of the space they're merging in. But the real magic lies in what happens at the moment of collision, the final fraction of a second when the two event horizons touch and become one. During this brief moment, the signal reaches its peak, a burst of gravitational energy that rings like a bell being struck. This ring-down is not random. It follows precise patterns, like the harmonic vibrations of a tuning fork. And from those vibrations, physicists can test the very fabric of general relativity itself. Does the merged black hole settle into a shape and spin predicted by Einstein? Does it obey the no-hair theorem, which says a black hole is defined only by its mass, spin, and charge? So far, every test confirms Einstein's equations, but scientists are watching closely. One day, just one signal may ring out a note that doesn't belong, hinting at new physics, hidden dimensions, or even flaws in general relativity. The implications would be enormous. Even more fascinating is what these waves tell us about the expansion of the universe. Normally, we measure cosmic distances using light, from standard candles like supernovae or variable stars, but gravitational waves offer something new, a standard siren. Because the strength of a gravitational wave depends on the masses of the black holes and how far they are from us, scientists can directly calculate their distance. If the merger also produces light, which happens in neutron star collisions, they can determine its redshift and from that calculate the Hubble constant, the rate at which the universe is expanding. This provides a completely independent way to probe cosmology, and it's already leading to tension with existing measurements, suggesting something about the universe may be more complex than we thought. But we're not stopping at LIGO. The European Virgo detector has joined the network, adding a third ear to the sky. Japan's Kagra has added a fourth, and soon LIGO India will expand our reach even further. With more detectors spread across the globe, we can better locate where these mergers happen and alert astronomers to search for light, neutrinos, or X-rays from the same events. This is the new era of multi-messenger astronomy, and it doesn't end on Earth. Scientists are now working on LISA, the Laser Interferometer Space Antenna. Scheduled for launch in the 2030s, LISA will place 3 spacecraft in orbit around the Sun, separated by 2.5 million kilometers. They'll beam lasers at one another across vast distances, listening for the deeper, slower rumble of supermassive black hole collisions. These cosmic beasts, with millions or billions of solar masses, merge far less frequently, but produce waves that ring across the universe for hours or days. LISA will hear them long before they collide, giving us a cosmic countdown to a truly titanic explosion. What once was silence is now a symphony. From chirps that last a second to rumbles that stretch for weeks, we are listening to the heartbeat of the universe itself. Picture this: 2 black holes, each the size of a small city, but with masses tens of times greater than our Sun, spiral toward one another in a deadly dance. They've been locked in this orbital embrace for eons, maybe since the very birth of their galaxy. Each revolution drags them closer. With every turn, they radiate gravitational energy, ripples that echo invisibly through the fabric of space-time. Time itself stretches and warps around them. And in their final moments, just before the cataclysmic union, everything, their motion, the warping of space, even the beat of time, reaches an unbearable crescendo, and then collapses into a singularity of unimaginable power. This is the anatomy of a black hole collision. It starts quietly, cosmically speaking. 2 massive stars end their lives in supernovae, leaving behind black holes. If they're close enough, they become a binary pair, locked in orbit by their mutual gravity. Over millions, or even billions of years, these black holes slowly spiral inward. At first, this orbit seems frozen, so vast is the distance between them. But every orbit emits gravitational radiation, tiny distortions that carry away energy. Slowly, ever so slowly, their dance tightens. This phase can last longer than the age of modern humanity, but the real drama begins in the last few seconds. At this stage, the black holes are moving at incredible speeds, up to half the speed of light. That's nearly 150,000 kilometers per second. They whirl around each other dozens of times per second, stirring space itself into a vortex. Their individual event horizons, the points of no return, begin to distort, elongating and merging like drops of oil in water. In the final orbit, they complete one revolution in mere milliseconds. Tidal forces grow so extreme that even light is bent into a pinwheel, what's known as gravitational lensing. If we could observe this directly, we'd see ghost images of the black holes circling one another, reflections of warped space seen through time itself. This isn't just science fiction. It's a prediction of general relativity, backed by simulations and mathematical precision. Then, the moment comes. The event horizons touch. In a flash, the 2 singularities merge, forming a new black hole, larger and more powerful than either predecessor. But not all the mass survives. A few solar masses are obliterated, not converted into light, but into pure gravitational wave energy flung outward in all directions. This burst of energy for that split second exceeds the power output of the entire visible universe. Think about that. All the stars in all the galaxies, combined, do not outshine this single moment. But it's not light we see, it's a chirp. Final rising note in the gravitational waveform, like the closing beat of a cosmic drum. This is the moment scientists at LIGO wait for. It's over in less than a second, but it contains the signature of creation through destruction. What remains after the merger is a new black hole, now ringing like a struck bell. It goes through a process called ring-down, where its distorted shape settles into a stable form. This produces a series of decaying gravitational waves, much like the sound of a bell fading into silence. These waves tell us about the final mass, the spin, and the stability of the new object. From them, we can test whether Einstein's predictions still hold true, but what if they don't? The real mystery lies in what we don't see. General relativity says that once a black hole forms, its internal structure is forever hidden behind its event horizon. But quantum theory disagrees. It suggests information can't just vanish. This leads to one of the greatest puzzles in physics, the black hole information paradox. When two black holes collide and merge, is information about their original quantum states lost forever, or is it somehow encoded in the gravitational waves or preserved in ways we don't yet understand? Some physicists propose that during collisions, exotic quantum phenomena may momentarily occur near the event horizon, such as firewalls that defy classical physics or echoes in the gravitational wave signal that could hint at quantum effects. So far we haven't detected any such echoes, but scientists are listening. Every new black hole merger adds data to this cosmic experiment, potentially pointing us toward a unified theory of quantum gravity. And then there's the unexpected. In 2019, LIGO and Virgo picked up a signal that didn't quite fit. It was a merger, yes, but one black hole was around 23 solar masses and the other only about 2.5. That smaller object was too heavy to be a neutron star and too light to be a black hole, according to our understanding. It fell into what we call the mass gap. Its origin remains a mystery. Was it an exotic star? A primordial black hole formed just after the Big Bang? A sign that we need to revise our stellar models? Nobody knows. Other detections have revealed black holes spinning at unexpected angles, like dancers tumbling through space off-axis. This suggests that not all black holes are born peacefully in isolated binaries. Some may form in crowded stellar environments, like globular clusters, where interactions between stars are frequent and chaotic. In these environments, black holes can capture one another through gravitational encounters, forming binaries that are misaligned, eccentric, and unpredictable. There's even evidence, though still speculative, that some mergers may be part of a chain, where a black hole formed from one merger later merges again with another. These second-generation black holes could grow rapidly, accumulating mass and spin. In time, they might even become seeds for the supermassive black holes that lurk at the centers of galaxies, which brings us to the frontier. Collisions, not of stellar mass black holes, but of titanic, supermassive ones. Imagine two galaxies colliding, a process that takes hundreds of millions of years. Their stars rarely crash, but their central black holes are on a fatal trajectory. Over cosmic time, they spiral together, bound by gravity and the pull of surrounding matter. Eventually, they, too, will merge. But the energies involved are staggering. Millions or billions of solar masses converted into gravitational waves. These waves are far lower in frequency than LIGO can detect, but perfect for LISA, the upcoming space-based observatory. When LISA launches, it will listen to these slow, deep tremors. And it might even allow us to predict black hole mergers before they happen, giving telescopes a chance to catch the aftermath in light. This would be a cosmic first, seeing, hearing, and studying the most powerful explosions in the universe. As they happen, we're not just witnesses to black hole collisions, we're participants in decoding them. Each event tells a story, of formation, of evolution, of violence and symmetry, and the secrets of space and time. And the more we listen, the more we realize the universe is not a silent void. It's a grand roaring opera, and black holes are its loudest performers. As we reach the final chapter of this cosmic journey, consider this. Every collision of black holes is more than just a violent event. It is a bridge between two epochs. It's a reminder that in the vast expanse of the universe, everything is connected. The black holes themselves, their births, their spirals, their fates, hold the answers to questions we've been asking for centuries. How did the universe come to be? What are the fundamental laws of nature? And most intriguingly, is there a deeper order that governs the chaos? The merging of black holes is not just about the death of two objects, it's the birth of something new. A new black hole, a new mass, a new cosmic footprint etched into the fabric of space-time. The event creates ripples that we feel, that we measure, that we study. But these ripples are not just the aftermath of destruction, they are the echoes of creation. Because every time black holes collide, they give birth to new possibilities, new insights into the universe's grand design. But perhaps the most awe-inspiring aspect of black hole mergers is the realization of how little we truly understand. Despite all the data we've gathered from gravitational waves, simulations and observations, the mysteries that arise from these collisions continue to perplex us. Every discovery only leads to more questions, like a never-ending cycle of cosmic curiosity. It's like staring into an infinite abyss and knowing that the more we learn, the deeper that abyss becomes. What happens in the heart of a black hole? Can we ever hope to understand the true nature of space-time? What is the fate of the information that falls into a black hole? These questions might seem unanswerable today, but perhaps tomorrow we'll find the answers, just as our predecessors uncovered the secrets of light, gravity, and the universe itself. This journey into the depths of space has shown us that black hole collisions are not just a spectacle of destruction. They are profound events that challenge the very fabric of physics. They reveal to us the stunning, incomprehensible forces at play in our universe, forces so powerful that they transcend our understanding of reality. And yet, in their quiet aftermath, they leave us with more than just a black hole to study. They leave us with a new perspective on the universe itself. Now imagine, what if we could harness the knowledge gained from these cosmic collisions to unlock even greater mysteries? What if understanding the mechanics of black hole mergers could lead us to uncover the secrets of dark matter and dark energy, those elusive forces that make up most of the universe but remain completely invisible to our eyes? What if this understanding could someday allow us to peer into the very heart of a black hole, or even manipulate space-time itself? These questions may sound far-fetched, but the truth is, every groundbreaking scientific discovery has started with a question that seemed impossible to answer. And now here's where you come in. Every great discovery, every monumental leap in understanding, starts with a few brave explorers, scientists, researchers, and curious minds who dare to look beyond the horizon. Right now, Cosmic Whispers is just beginning this journey, and your support means everything. If you enjoy unraveling the mysteries of the universe with us, hit subscribe. It's free, and it helps us grow this community of cosmic explorers. Together, we can continue to push the boundaries of human knowledge. We've covered the science, the discovery, the wonder of black hole collisions, but our journey is far from over. There are countless more mysteries lurking in the farthest reaches of space, waiting to be uncovered. And the more we learn, the more we realize that we are not just spectators in this cosmic drama. We are participants in something much bigger, something vast, mysterious, and full of potential. And with each new discovery, we take another step, closer to understanding the true nature of our universe. So as we close this chapter, remember, the universe is not just a place of distant stars and black holes. It's a living, breathing entity. It's a place of energy, matter, and forces that we're only beginning to comprehend. And every time we look up into the night sky, we're reminded that there's still so much more to learn, so much more to discover. The only limit is the boundaries of our curiosity. Before we end, I want you to think about something. The next time you look at the stars or think about the vastness of space, Ask yourself, what secrets are still out there? And how far are we willing to go to uncover them? If you've enjoyed this journey through the cosmos, don't forget to like, share, and subscribe. And leave us a comment. What do you think lies at the heart of a black hole? Do you believe we'll ever fully understand them? Join the conversation, and let's continue exploring the mysteries of the universe together. This concludes our deep dive into black hole collisions, a powerful chapter in the story of the cosmos. Thank you for joining me on this thrilling journey into the heart of space and time. Keep your curiosity burning. There's always more to discover.